Good Monday, I guess? Woo, yes. Somebody had a case of the Mondays. Okay, so let's get right into it because we're actually really close to the end of this section. I'm actually like super impressed with how we're progressing on first follow sets and syntax analysis. So we will get right to it. Okay. So on Friday, we talked about how do we calculate follow sets. So what are follow sets? What are follow sets? What's the semantics of the follow function?
Anything that follow non-terminal.
Specify anything. Be a little more specific. So what?
Like terminal token.
Yeah, the tokens are terminals that come directly after a non-terminal, right? So it's what are possible tokens that can come after this non-terminal. And so the input is a non-terminal, the output is a set of terminals or the end of file operator, or the end of file. And so the way we do this is very similar to first sets. We start to initialize empty follow sets for all the non-terminals in our grammar. And then we go through each of these 5 rules, which we've been talking about the last, Wednesday and Friday, so about 2 classes worth. So we start with, the first rule is very simple. We start by adding the end of file to the starting non-terminal. We add the end of file to the follow set of the starting non-terminal. That's our first rule. The second rule says that if the non-terminal we're interested in this case A, is all the way at the end of the rule, then we know we can add the follow of the left-hand side non-terminal to the follow of A. Rule 3 says, hey, but if we're not the rightmost, and there exists epsilon in the first sets of all symbols between the token we're interested in and the end of the rule, then the same thing applies. And we could say we add the follow of B to the follow of A. Fourth rule says, whatever comes after you in the rule, right, your A, whatever comes after you, add its first set minus epsilon to your follow set. And the fifth rule says, well, you can keep doing this, assuming that C0 has an epsilon in its first set, then you can add C1. And if C1 has an epsilon, then you can add C2 minus epsilon. And if C2 has an epsilon in it, you can add C3, so on and so forth. Okay, so we went through and we used our handy-dandy rules and grammar that we've been using as an example so far. And we kind of went through, I think we were, something will stop me, I think we were like here, more or less. Okay, cool. So we just did A. So now we want to calculate the follow of B. So where do we look? What do we look at? I want to calculate follow of B. This is everything that I know that I've already done. How do I calculate follow of B? So specifically, so you said look at the first rule. How do you know I look at this first rule? Yeah, we look for every instance of B where in the rules? On the right-hand side. Boom. So we look at the B here, and so we ask, does rule 1 apply? No, B is not the starting non-terminal. Rule 1 does not apply. Is B the last element of the rule, the rightmost symbol in this rule? No. Nope, doesn't apply. Does epsilon exist in every symbol from B to all the way to the end of this rule? Yes. So C and D, C has epsilon in its first set, D has epsilon in its first set. So then I add what to the first of B? Follow of S to follow of B, exactly. And then rule 4, so which symbol does rule 4 apply on? Which is C0 in this example? C. So I'm going to add the first of C minus epsilon to the follow of A, or to the follow of B, sorry. So this will give me the first of C is C epsilon, subtract out epsilon, we have C. So now our follow of B contains the end of file, C, and then we have to say, does rule 5 apply? So does rule 5 apply? Does epsilon exist in the first of C?
Yes.
Yeah, so then I add the first of D minus epsilon to the follow of B. And so the first of D minus epsilon is the set containing D. And we have no more, we can't add, there's no more rules there. So the follow of B should be end of file C and D. Cool. Questions on that calculation? All right. So now I want to calculate the follow of C. How many different rules do we have to look at? 3 different rules, right? We have to look at every single rule where C exists on the right-hand side. Specifically, every instance of C in the right-hand sides of this rules. Right? So we go through apply all the rules. We know, so C is not the starting non-terminal. Is it the last element? No. Could it be the last if there are epsilons in every symbol that comes after its first set? Yes. So we add the follow of S to the follow of C. And then we say we add the first of the one that comes after it, so the first of D to the follow of C. So the first of D is D. The first of D minus epsilon is D. And does rule 5 apply here? Yes. So what do I add? Maybe nothing. What was that? End of file?
Follow page.
But this doesn't say anything about doing follow. This says as the first of something to follow A.
First of D.
Say it again?
First of D to follow up C.
So we did first of D here for rule 4, right? Rule 4 says always do the next one. So rule 5 says can I do the one after that? So why does rule 5 apply or why does it not apply?
Not apply is nothing is happening.
Now, there's nothing there. There's nothing after D, right? So it doesn't make sense to add the first of the next thing, which is nothing. Right? There are no symbols here. So one way you can think about it is C is A in this case. I would be 0. But what's I plus 1? What's C1? It does not exist, right? So this rule doesn't apply. The rule is not in the form of the non-terminal I'm interested in, and then I plus 1. There is no plus 1 anymore. Okay, so that's it there, but then we also have to apply these rules in the second rule. A goes to CD. So once again, I say, are we the last element? No. Could we be?
Yes.
Yes, so we should add the follow of what to the follow of C?
A.
Yeah, the follow of A to the follow of C. So that's going to add B to the follow of C. And then by rule 4, we need to add the first of D minus epsilon to the follow of C. And does rule 5 apply?
No.
No, by the same logic we just talked about, right? Can't possibly apply. Cool. I have to look here. Am I the last?
Yes.
Yes. So what do I add? Follow of C to the follow of C. How do I know the follow of C? Do I explode in an infinite loop? What do I use as the follow of C? What was it? Empty set. I use the last knowledge that I have of C, which is the empty set. Right? I am currently calculating the follow of C. Right? And anytime I need to reference it, I have the previous value I can pull from. That's why we start with empty sets for all the initial follow sets. Sweet. Okay, does rule 3 apply? Why not? There's nothing after, right? This says you have to have something after. If there's something after, you add its first set minus epsilon to your follow set. There's nothing afterwards here. And by the same token, 4 doesn't apply and 5 doesn't apply. There's nothing afterwards. We're at the very end. Cool. So we should have the follow of C is end of file D and B. Then we calculate D. So D, once again, we can look at 3 different rules. This should be easier. Does rule 2 apply? Yeah, we're the last element. We are D. We add the follow of S to the follow of D. We're good. None of these other rules will apply because we are the last element. There's nothing that comes after us in this rule. What about for this rule? Yeah, same reasoning, follow of A, right? The second rule applies. We add the follow of A to the follow of D. And none of these other rules apply because we are the last element. Cool. Okay, follow of D. Same thing. Nothing changes. So we get follow of D is the end of file B. And then if we do all these again, we'll get the same answers. And so we said we've gone through every non-terminal, applied every rule we have, and nothing changed. What does that tell us? We're done. We can stop. So now we have first sets and follow sets for this grammar. Awesome. Everybody good on first and follow sets? Oh yeah, that's the correct answer.
There's a question over here.
Oh, sure.
Why do we have to do that last step?
Why what?
Why do we have to have that last column on the?
Oh, when we get here, we said, did we make any changes?
Yes.
Yeah, right. We added new follow sets, so we have to go apply the rules again. We don't know if something is going to change. We can only stop when we go through every non-terminal, apply every single rule we have, and we don't get any new information. That means we're done. Cool. Any other questions on this example? All right. So now we get to the why are we doing this? Right? So we want to build, so we started off this syntax analysis, we'll start at this first set by talking about parsing. Right? We wanted to be able to write a parser. So what is a parser?
Turns a stream of tokens
Into?
into a yes/no as to whether or not something's syntactically accurate using a context-free grammar.
Close. Yes, it does one additional thing in addition to that. What was that?
It creates a
Parse tree. It creates a parse tree, right? We want that, yes, it is syntactically correct, and if it is syntactically correct, we want the parse tree that corresponds to that sequence of tokens. Cool. Okay, so there are many different types of parsers as we talked about. We are going to study and talk about a very particular type of parser, predictive recursive descent parsers, which seems like a lot of words, so let's break it down. Predictive, what do we think that means?
It works.
I think that would be like correct.
I will guess what the next person.
How many tokens do we think it has to look ahead? And this is a good meta thinking about what have we been studying the past 2 weeks.
2.
2 what? So when we're trying to parse a non-terminal and say, okay, we want to parse, let's say, an A or an S, like in this case, we want to parse an A, we need to make a decision based on the tokens that we're seeing. Is it A goes to CD or A goes to little a, big A? Right, so predictive in this sense means by looking at one token, just peeking at one token ahead, can I decide if the rule is A goes to CD or A goes to little a, big A? And so that's the predictive part is where we get efficiency because we don't want to have to try all possible combinations of all rules, even though we know that will work eventually. What we want to do is know which rule to choose just looking one token ahead. So predictive, what about recursive? Yeah, it's recursive. It's just what it means. It's not supposed to trip you up or anything. So we'll see how it looks in the code, and we started that a little bit, but you'll see that it looks very recursive. Descent. Top down. We're going to start at the top. So we're always going to try to parse S at the top. And then we're going to figure out which one of S's rules apply. And then when we try to parse A, we'll figure out which one of its rules apply, and so on and so forth. Cool. So, and this is where it's important when we talk about no backtracking. So here, for each grammar rule that we have, when we have a choice, does A go to B or A go to C, we want to make that decision just looking at one token ahead, and we will never backtrack and change that decision. Okay. So what are some that we've actually been deriving the conditions for a predictive recursive descent parser. So what was some of the first ones? So my goal is I can only look one token ahead. And I have A goes to, let's say, alpha, and then I have another rule, A goes to beta. So I need to look one token ahead. What must be true about the context-free grammar in order for me to be able to write a predictive recursive descent parser?
First of all, alpha and beta should be different.
Yeah, so the first rule. So the first of alpha intersect with the first of beta. Better be the empty set, right? And this is exactly why we did first sets. By looking one token ahead, we can say, aha, it's got to be A goes to alpha and not A goes to beta. And I know because I calculated the first sets, and the first sets tell me all possible strings that alpha generates start with these tokens, and all possible strings that beta generates start with these tokens. So if I read a token, I'll be able to know exactly which rule generated that token. Cool. But then we ran into problems, right? What happens if epsilon exists in the first of, let's say, A? Right, we have an example, S goes to, I think, AS or epsilon, is that it? I think so. So what's the first of AS? A. And the first of epsilon? Epsilon. Check. Passes the first rule. But if I just read one token, if I read a single A, oh, maybe we need to change it. There we go. If I read a single A, does that tell me which of these rules I should have? No, I don't know if this rule happens again, or if I should go to nothing. Why?
There's a non-terminal after S.
Yeah, there's a non-terminal after A is the same of S is the same as what S could start with. Right? So whatever comes after S could also be what S starts with. And in the case of epsilon, epsilon can go to nothing, so I can't tell just from looking at one character ahead, does S go to epsilon or does it go to a different rule? So if epsilon exists in first of A, then it better be the case that the first, oh, that's so bad, sorry. That first of A intersect with follow of A better be the empty set. Do I have to rewrite, should I rewrite this rule here, this guard, to say that, like, if epsilon exists in alpha or beta, one of the right-hand sides? Why not?
Don't the constructor, don't the rules that define first sets take care of that?
Yes. But why would I care if it's alpha or beta? So yes, you can think the first of A is going to contain the union of the first of alpha and the first of beta. It's definitely true. Do I have to worry about epsilon being in the first of alpha and the first of beta?
No.
Why not?
Is it the first rule?
Because of the first rule. Yeah, this first rule says they're going to have nothing in common. And so I know one of the rules, if epsilon exists in the first of A, I don't really care which rule it is, but I know it's only going to be one of them. And then I say, well then, I'll know when to go to epsilon if I read, if what comes after A is never the same thing as what A can start with. And that's it. That's all we need. Boom. Is it exactly right? Yeah, that is right. Cool. So these are the rules. So I can give you any grammar. I can say, does this grammar support a predictive recursive descent parser? How should you show that? If I just give you the grammar?
Construct the first and follow sets?
Yeah, you have to construct the first and follow sets to the grammar, and then show for every rule where you have for rule 1, at every place where you have a choice, right? A goes to alpha and A goes to beta, then it better be the case that there's no intersection there. And you shouldn't show that. Here's some of the things you should not do. Just write yes or no. Other things you should probably not do is write these rules. Right? That doesn't actually show me that you know how to apply them. It just shows me you know how to read and memorize these things and copy them onto a test. Right? But it's actually applying these and say, how do I apply this to a context-free grammar to show that it actually does support a predictive recursive descent parser. Cool. Questions on this? You'll have practice in the homework, don't worry. Okay. Now we get to the grand finale where we can actually write a predictive recursive descent parser. And we're going to write that using first and follow sets. So, first thing we need is a context-free grammar, right? It doesn't make sense to talk about a context-free grammar. That's not, that's what we're doing. We're parsing, we need some kind of context-free grammar. Calculate first and follow sets. That's why I've been going over this, right? You can calculate first and follow sets. You want to show yourself or demonstrate to yourself, demonstrate to me often, that the context-free grammar actually allows a predictive recursive descent parser. And then we can actually, once we've done this, we can use the first and follow sets to write the predictive recursive descent parser. All right. Let's look at an example of this. So let's go back to our language that we've been using. Definitely not going to work the way I want it to. Oh, there we go. Sweet. Okay. So I'm going to write this like code. I am going to write code. So I start from the top. I have my parse.s function. What else do I need to be able to write this context-free grammar? This parser. Do I just need this? What was that? The production rules. Yeah, I need, well, sorry. Wait, what? I hit myself. These are the production rules. What else do I need? What was that? First sets, follow sets. I need all the follow sets, yeah. If I don't have these, I got nothing. Can I do it like this? No, of course not. That would be too easy. Okay, what's the best way to copy these follow sets? There we go. I have no idea what's going to happen when I paste this. All right, well, I copy paste all of these things very slowly. I suppose I could write it by hand, but I feel like this is still faster. Okay. So I'm going to write parsev. There we go. Wish I could like move these. Do you think there's? I guess I don't know this program that well. Oh well. What can you do? Okay. So actually now I'm going to draw because that's going to make it more confusing. Okay. So I want to write the parseS function. So do I have a decision to make here?
Yes.
Yes. What decision?
Check the conditions.
Huh?
Get the token and now we have to
So there's a couple things. I guess a little bit ambiguous, right? So when I say do I have a decision, one thing I'm asking is there a choice? Do I have S goes to two different rules?
No.
No, it's only ever going to go to one rule. But can I know right off the bat by reading one token whether this string actually corresponds to something that S could generate? No? So what if I told you that the very first token of the input string starts with an E. Could I know that this string, or what if I got end of file? What if the input string is the empty string? So can I know this just by looking at one token? And if so, how? Look at the first set of S. What does the first set of S tell us? Yeah, it must be either A, C, D, or B. If it's not one of those, then I can say it's a syntax error right away. Right? So I want to do t-type, GetToken. So if t-type is A, or t-type in tiny font is B, or, and I guess I'm writing or is more Python than C, but you know, however you, this is more pseudocode than real code. Let's see, A, B, C, D.
So
Yes.
if we already have set operations, we could have said if the intersect of first of S and t-type is not empty.
Yes. Or you could say, if you have sets, you could do if t-type exists in this set, in the set of first of S. Yes. Okay, so if it is, then what do I do? What should I do? Now I have to actually think about how do I parse this rule? I already essentially did that here, right? I mean, I don't know what parseA is going to do, right? So let's think about what are the semantics? What should this parses function actually do? So what are our two goals with our parser that we want?
Valid syntax and a parse tree.
Valid syntax and a parse tree. So parses should probably throw a syntax error if there's a syntax error, right? Right. So let's go all the way down here. We'll say else. We'll assume we have some function called syntax error. Right? We'll just assume that it's going to terminate execution and print out an error message. Okay, so I know right off the bat, if I parse something, it's not an A, B, C, or D, then I can say right away it's a syntax error. Great. So what else should I do?
We have to find a way to store the derivation, because if we forget that we used, well, we know we're going to use S, but if we just get another token and check that, we need to remember.
Right, so one key thing is we only want to look one token ahead, right? We've already, and when we call GetToken, what does the lexer actually do? Yeah, it consumes that token from the input string, so the next time we call GetToken, it's going to consume more of the input, and the next time we call GetToken, it's going to consume even more of the input.
So we need a GetToken first.
Right, so there's a couple things here. So we're going to, let's ignore the actual creating of a parse tree in a second. We'll see kind of how that will come about in the way that we're creating this. But for now, so this parses function is responsible for parsing an S, right? Creating, you can think of it in a couple different ways. Verifying the input where it has and verifying that that input came from a parse S. But does it have to worry about checking A or B or C or D? If we have a parse S function, what do we assume we also have? Parse A, parse B, parse C, and parse D, right? Those are all functions we will have to write, but we can rely on them. So if I know the rule is S goes to A, B, C, D, then what is the first thing I know that should happen there? Parse A should happen, right? And that function is responsible for parsing an A from the input and moving the tokens until after that parse A. And then what happens after parse A? Right, and because we already talked about each of these parse functions is responsible for checking that its little chunk of the tree is semantically valid. So if parse A successfully returns, then we know we have successfully parsed an A, and that's it. And that the next time we read a token, it should be from B, but we know that we are syntactically good at this point. So now I have to parse a B, parse a C, parse a D, and then when I get here, what do I know? Yeah, that's your point. Just a second. Yeah.
Quick question. So I know that your else for parsing S, you have to return a syntax error and fix the program, but what would the else statement on parse A, B, C, and D return?
They don't return anything for right now. So because we're just thinking of them as a little bit more abstract. We can think they'll do whatever. They'll construct the tree for us. They'll do this much more in depth in project 5. But for now, we can think they just do whatever they do. They'll call syntax error if there's a syntax error in their part of the tree. Otherwise, they'll just return. Cool. Yeah, now what do I need to check after this?
At the end of file.
Why do I need to check end of file?
Parse D is the last symbol in parse S.
Yeah, I know I have. Right? I know I have this S goes to A, B, C, D, which means if I have A, B, C, D, if there's anything else after that, it's going to be a parse error. Right? So now I want to actually add in here, I'm going to do a little, let's see, look at my drawing skills are. Kind of like a zoom in thing. I'm also going to get rid of this because you're so. Okay, terrible GetToken. If T type is, what do I care about here? Yeah, is not equal to the end of file. If it's anything else, then I know it's a syntax error. And all that goes in here after this check. So now what about at the top? So I'm calling parse A, but I just read in a token that was either an A, B, C, or D. But where did that actually come? Did that come from the rule S goes to A, B, C, D? Is it one of S's children in the parse tree? No, where did that come from? Yeah, from either first of A or B or first of B, right? And so it's actually not our responsibility to parse that and to move that input. So we need to make sure that we actually put that back. Right? Because we are not actually consuming that token. Cool. Questions here? Yeah.
So is the main function. So who's going to call S?
The parser.
So it's like the main function.
Yes. Yeah, it's like the entry point. Yes.
And maybe this was asked, I wasn't paying attention, but are we storing the tree? Because you said the parser returns yes, no, one, the syntax is valid, and it returns the tree, but we're not building it.
We're not explicitly creating a tree, but as you'll see, this series of function calls create the tree.
But we don't need to store.
Not right
like
here.
full
Right.
data structure is what we
Not
store.
right now. Right now, we're just worried about creating the structure so that later we can do whatever we want, right? So later when we get here, we know, hey, I probably parse S goes to A, B, C, D. Now I can choose whatever I want to do here. Maybe I want to create the tree. Maybe each of these return nodes that I'm going to create into a tree structure. You'll get into this a lot more in Project 5. But for now, we want to think about it a little slightly more abstractly. Cool. Okay, let's take parse B first. That one's a little easier. Okay, what do I need to do parse B? What was that?
Just get the T type is with GetToken.
GetToken and then what?
Compare it to B to more B.
First of B.
And what if it is?
You should just like go back like we go.
And then what? What if it's not though?
SyntaxError.
Yeah. So maybe we can rephrase this. T type is not equal to B. Syntax error. Right. So here I'm throwing an error, and then here we can print maybe something that says, "Hey, I just parsed B goes to little b." Or whatever. Right. So this would be where you do whatever you want to do when you know that this rule occurs. Like here, I'd probably put print S goes to A, B, C, D. Right? Because I only know that this rule was successful when I get all the way to the end here. Sweet. Okay, so B is really easy, but why didn't I call UngetToken like I did here?
You should parse B now.
I've actually parsed B, right? B, the rule big B goes to little b, this actually creates the B in the input. And I know, okay, now it must have, this is the correct rule. And that way when B returns, we say, yes, we've parsed this B. And now everything after that will start on the next token following that. Okay, let's do D. Okay, gotta get the token. Always gotta get the token. Okay. So now what I check for with D. Something falling all the way down. It's like when you spill like Skittles or something in a movie theater and it falls. Okay. So we need to call this parse D rule. We want to create this parse D. So then how do I distinguish between these two rules? By looking at first of capital D? First of capital D is D epsilon. So how does that tell me? What do I check? How do I choose which of those rules? Somebody want to raise your hand? Sorry. A lot of you. No? You just all want to talk at once. Harder to be wrong. Yeah?
We could just check that the next symbol is D, then we can say that that rule has been applied, and if it add one to epsilon, then we could check the follow.
Yeah, so if we get a lowercase d, right, then we know which one of these rules must have happened. We have this one or this one, one or two? One. We know rule 1 must have happened. Why? Because if this rule occurs, what did we actually read from? Yeah, the follow of D, which is end of file or B. Right? And we actually didn't go through it. We probably should have. But we didn't go through and calculate the first sets of CD and the first of A to make sure there was no intersect, and also we didn't go through everywhere there's an epsilon to be able to determine which one of the rules we allow. But oh, I'm pretty sure it's good. C, B, B. Yep, that's good. A. Yeah, okay, we're good. Okay, so I know if the token is what? D. Well, okay, so yeah, that's a good point. So why can't I say D or epsilon?
You don't have a string yet.
Yeah, we GetToken only returns tokens or end of file. It never returns epsilon, right? Because we saw GetToken, right? It's just doing lexing and it's trying to find the longest token that matches. It's either going to return that token or an error. In this case, it's going to be a major error. I mean, nothing's going to work. Or it will be end of file. That's it. Those are the only options. So if we read a lowercase d, then what do we know? Which rule is it? Rule 1 or rule 2? Rule 1. I do what? UngetToken like before. That work good?
Why do we want to UngetToken?
Well, that's what we did before.
But then we parse the D.
Yeah, so we actually don't want to call UngetToken here. Why?
We just consume the little lowercase d.
Yeah, because we produce this lowercase d, right? This specific production rule, this instance of d. So we want to call UngetToken. Otherwise, we're just going to loop infinitely. We're never going to reach the end there. Okay, let's see if I can move these up. Success. Look at that. Cool. Okay, so then what else? So how do I know it's this rule 2 as opposed to a syntax error? The what? Follow of D? Yeah, so if it's an end of file or a B, then that means it must be B, D goes to epsilon. Otherwise, it's a syntax error, right? It has to be one of those things. Otherwise, it's not syntactically valid. Let's see, I'm going to be lazy, and I'm going to start writing it like this. $. Was it B? $B? Which just means, is t-type one of these two? Then what? Why do I want to UngetToken?
You don't actually consume epsilon.
Yeah, right? The rule is D goes to epsilon, right? Which means it went to nothing, which means we should not parse anything from the output. There should be nothing that this parses from the output, so we want to unget the token. Cool. Okay, then if it's neither of these two rules, right, we just did both of these two rules. If it's none of those, then it must be what? Syntax error, you made a mistake. Okay, then let's do ParseA, because ParseA is very interesting. Okay, so now we're going to look at ParseA. When I have two rules, A goes to CD or A goes to A. A goes to little a, big A. So I'll let you guess, what's the first thing we do? Get a token, yay. So then how do I distinguish between these two rules?
Choose to look at if else with them.
Say it again?
Just if else on them, so if it's CD, do this else.
If it's CD,
Yeah.
but big C is big D?
Big C, yeah.
But I'm never going to read in big C or big D, right? Those are non-terminals, so I only read in terminals. What was that? Let's put somebody over there. That area. Oh, you're out of that area. You're going right there. Somebody over there, what do I check for? What was that? Little a? And what does that tell me? That's the second one, so I have two rules, 1 and 2. So then how do I know if it's the first rule? And then how do I know if it's a syntax error? What was that? The first rule would be little c or little d. Or epsilon, so then what do I do? Yeah, so I should also check the follow of what? A, which would be B. Right, so the first one, the rule 2 is easy, and we'll write that first since it's easier. So if t-type is an A, then I know the rule is A goes to little a, big A, new line. So then do I call UngetToken? No, because I want to parse this A, right? It existed here. Great. And I call what? Myself, I'm recursive, right? So if I didn't read an A, and I wanted it to be the rule A goes to CD, right? Let's think, what's the first of CD? C, D, epsilon. And then we know the follow of A is B. So we know that it's either going to be a C or a D, in which case it's in this rule. Or if this rule went to epsilon, we need to check, is it in the follow of A? So it should be a B character. Right? So C, D, B, because I can't check epsilon. What do we say? C, D, E. Then what do I do? Do I UngetToken or keep the token? Unget, yeah. I don't generate this token. Parse C, and print that, hey, I chose the rule A goes to CD. And what if it's neither of these? Syntax error, error rule. Cool. And so we did everything except for C, but we could do C very similarly. Question, yes?
So each of these parse functions makes up our parser.
Yes.
And each one is distinct. You need a different parse function for each non-terminal in your grammar.
Yes.
So if I'm not mistaken, in project 3, we're supposed to read in a context-free grammar.
Yes.
And then read in a string of tokens to determine if it's in the grammar.
No.
No, we're not doing that.
All you're reading, for project 3, you're reading in the context-free grammar, and you are calculating first and follow sets for that grammar and other things.
In the event that you would have to do that, how do you dynamically develop these parse functions?
Different ways. People do it in different ways. There's tools like Lex and Flex and like Bison and stuff, which will actually You give it input in your context-free grammar, and it generates C code, C++ code, that implements all these parsing functions. So yeah, that's part of what you're seeing in Project 3 is you can do this all programmatically. Right? So you can calculate first and follow sets programmatically, and you can generate a parser programmatically. You can do everything programmatically.